Hi, welcome to the first substantial video on combinatorics. Insofar as these videos follow the textbook, I'm skipping chapter 0. That is mostly material that I assume a viewer would have already seen somewhere else, and reading that chapter as brush up should hopefully be relatively easy, so I'm just going to jump into chapter 1. So this is enumerative combinatorics, making combinatorial arguments, and this video is really going to be a short video focusing on some rather fundamental and not very, possibly not even very interesting, right? These are things that the viewer likely has already seen also. But there are a few things to talk about. First of all, I like using this square union symbol. Not everybody, right? There may be a significant number of people who have not seen that symbol. It is the same thing as the union, right? So when I write this square union symbol, A square union B, right? A and B, some sets. By the way, finite sets in this video and probably every other video in the combinatorics series. I don't know if we'll ever get around to talking about infinite sets, but in any case, at least for the first several videos and possibly for all of them in the combinatorics series, we can assume that these sets are finite. Not that that matters for the square union, but anyway, A square union B is exactly the same thing as A union B. They have exactly the same elements. The only difference is that the square union also asserts that A and B are disjoint. So it's, right, what it is a set with exactly the same elements as the union, but it also carries with it this assertion. And it's nice to have this assertion because in combinatorics, but also several other mathematical topics like measure theory, a lot of the theorems that we state are valid only for disjoint sets. And so it's nice to represent that the sets are disjoint so that we're reminded of it while we're working on these sets, and we are reminded that the theorems, which are valid only for disjoint sets, are valid for these sets. So it's nice to just see it in the object while you're working with the object. So that's the square union. Okay, a first instance of exactly where that kind of thing comes up is with the sum principle. It's a very obvious principle. It says that if you have some two disjoint sets, or another way to think about it is you start from a set and you partition it into two partitions, right? Either way, one way or another, find yourself with two disjoint sets. You're trying to enumerate their union. Of course, you could just union it, like in this case, get 7 elements, and so the cardinality of the union is 7. The sum principle says that you could just as well have enumerated A, then enumerated B, and then take the sum. So, right, 3 plus 4, 7. Here's a very simple, obvious application of this, right? If this seems too easy, it's because it is. It's not a deep principle per se, but it's one that we'll be using a lot. Notice that disjointness is strictly necessary if you ever have finite sets which are not disjoint, and yet you try to follow the principle anyway, you will count it wrongly. In this particular example, the set actually has 2 elements, but if you followed the formula not respecting the fact that they're not disjoint, you'd be led to calculate 2 plus 1, and that's wrong. Of course, I've only written this for 2 sets, but there's an easy generalization to any finite disjoint union of finite sets. I take it the generalization is so obvious that I don't need to spend any time on it. Moving on to the next super basic principle, there's the fundamental counting principle. That's what I call it. I think several other authors also call it that. The textbook author calls it the product principle, which lots of people also call it the product principle. So either name is fine. I like the fundamental counting principle to almost see it as the fundamental theorem of this subject, but or at least a fundamental tool, I suppose. Anyway, either name is fine. It says, right, this principle says, if A and B are finite sets and we want to find the cardinality of their Cartesian product, then again, right, you could either directly enumerate it, that's what's expressed on the left, or you could enumerate the first set, then the second set, and take their product. So it's a formula for enumerating the Cartesian product. I've given a simple example here. Notice that this demonstrates that in this principle, we don't require disjointness. If we took a product of two sets, each with two elements, then the Cartesian product ends up having 4 elements, but you could have enumerated that as 2 times 2. A brief word about permutations that the textbook does not bring up. And this is not an important thing, so if this is a kind of nitpicky technical point that you don't care about, then you can feel free to skip this part of the video. But I did want to point out, this is at least the kind of thing that I like to try to make sure that I understand all the details of everything as much as I can. And so often an author will claim that the formula for counting permutations, right? If you have a set of size n and we want to find all permutations of the n elements taken n at a time or something like that, right? It has the formula n factorial. And we often claim that this is a consequence of the product principle. And it sure seems like it kind of feels like it. You say, how many choices are there for the first element, n? How many for the second element after the first has been taken already? Well, n minus 1 elements remain, so multiply, seems like the product principle, by n minus 1. Now, again, this is a bit of a nitpicky issue, but you can't strictly apply the product principle, having defined the product principle in the way that we have. Some people don't define the product principle quite so technically. It's more of a sort of open-ended philosophy of enumeration or something like that. But if you define the product principle in the strict technical sense that we have here, then you can't pick any set A and a set B such that the set of all permutations, right? Let's by the way recall, what is a permutation? Imagine that we took the set 1, 2, 3, and we're looking for all of the permutations of these 3 elements. Well, one permutation would be the ordered list 1, 2, 3. Another one would be 1, 3, 2, and so on, so that you can view the permutations as ordered pairs such that every element occurs exactly once. So that's what a permutation is for an n element set taken n at a time or something like that. Anyway, and there is no set, right? Like this set is not equal to any A cross B cross C, and therefore a direct and very flat-footed application of the fundamental counting principle does not count the permutations, right? So that's not the way, right? Like that's not the full justification for why the permutation formula is correct. Instead, right? What you could say is that there is, right? Like if we were to take, for instance, if we were to take the permutations of this set 2 at a time, right? So rather than 3 at a time, we take it 2 at a time, meaning that the set of permutations for this set taken 2 at a time would be 1, 2, right? 1, 3, 2, 1, and so on, right? That's the permutations taken 2 at a time. Although we cannot say that this, right, that this set is any A cross B, we could make a fairly simple argument arguing that its cardinality is the same as the cardinality 1, 2, 3 cross some 2-element set. I'll just write down 3, 4. Arbitrarily, right? 3, 4 has nothing intrinsically to do with this problem, but the point is that we could set up a bijection between the set of permutations and this set. And so, and then of course, when you do so, then you are, perhaps, right, if you do it this way, then you are using the product principle to enumerate that set. But anyway, so I just wanted, in case this was any source of confusion for you, as it somewhat was for me at some point, the permutation formula is not merely a direct application of that technical version of the product principle. Anyway, so tedious point over. Here we'll see an example. This example will use the enumeration of permutations. But anyway, I really thought this was a neat example. Like I was surprised to see this be the example right after the product principle was introduced. It looks a little intimidating, right? I mean, particularly because it has that pi symbol, which in undergrad you almost never see really, or perhaps rarely. Sigmas, yeah, but products tend to be harder to work with, and so you don't see it quite so often. And so this looks like this might be a tough example, but you dig into it, and it's really not. So just to get started, let's just see how this works. If we set n equal to 2, meaning that we have a total of 4 people, and we give them the abbreviated names A, B, C, D. Now, just to sort of brute force list out all of the matchings, right? The whole task here is to count how many ways these people could be matched with each other. And a matching will be a set of 2-element sets that partition the set of all people. So in particular, here's one matching, right? I can match A with B, right? Put them together in a set. And I can match C with D, put them together in a set. That is a matching of all people, right? So everybody is in precisely one of the partitions here, and each cell of the partition has 2 elements. So that's matching. And I've enumerated, right? I've listed all of the matchings. There are 3 of them. So so when n is equal to 2, the number of matchings should be 3. So how do we enumerate this in general? Well, for getting n equal to 2, let's go to the general case where you have any n, and therefore you have 2n people. If you grab any one person at random, this person must be in some unique pair. So how many ways are there to pair this person with someone else? There are 2n minus 1 people to choose from. So that's how many matchings exist for this particular person. Having made that matching, we remove these 2 people. Neither of them will be matched ever again. So then we look at a population of 2n minus 2 people. And then we do it all over again. We grab one of them at random. We look at all of the ways to match this person with anybody else from the population. So if there were 2n minus 2 people, we grabbed one at random. There are now 2n minus 3 to match this person with. So we get a factor of 2n minus 3, and so on. So Continuing likewise, eventually you get down to just 2 people remaining. There is only one way to match them. And so by using the product principle, right, the first factor is 2n minus 1, the next factor is 2n minus 3, continuing likewise down to 1. That's the formula counting this set, and it has this formula, it's the same thing to write it as this pi product. And so there you have it. Okay, next video we'll move on to the general philosophy of counting a single set in 2 ways.